Now here, if you look at this circuit, we need a lot of component, especially we need a 64-bit register and 64-bit adder, where we are trying to develop a 32-bit computing system, where we had already inside ALU a 32-bit adder, but for the multiplication purpose we need to have a 64-bit adder, which is a lot more lot more component in it, right? Question is, can we optimize this? Okay, can we make a simpler circuit? The answer is yes, we can. The circuit would look like this. Okay, so instead of putting the multiplicand in a left shifting 64-bit register, we keep it at a constant place. Okay, we don't shift it, we just keep it 32-bit multiplicand. Instead of multiplexer, we use a 32-bit AND gate. So inside 32-bit AND gate, you can imagine there are 32 and 1-bit AND gate. Okay, 32-bit AND gate, as we said, AND is a multiplication operation, so we don't need a multiplexer there. We just need an AND. Okay, and then we will use an adder, but 32-bit in this case, and we will have some special arrangement for the product register 64-bit, where it can be it can be shifted to the right. Okay, shifted to the right, and partial product in terms of 32-bit being stored into the upper half of that register. Okay, without affecting the lower half. So this kind of circuitry register we can make. Okay, so where we can tell this piece of hardware only partially load your upper half while keeping the lower half intact. Okay, but when we shift to the right, all this 64-bit will be shifted. Okay, and then of course we have to load it, like when this right signal goes to high, that's when this partial addition result comes into this 32-bit, which comes from the 32-bit adder. So this is a simpler circuit, okay, using 32-bit adder, but how it works, for that we need to understand a little detail on the multiplication strategy. Okay, the first step to understand that strategy, which enable us to actually compact down the digital circuit, what first we need to understand, shift is a relative term, right? So basically, when I am saying we are shifting the multiplicand towards the right when keeping the multiplier at the same place, that is same as keeping your multiplicand at the same place and shifting multiplier to the right. Okay, just think of in terms of the partial product and then how we are writing the product at the end step. So let's say at some step I have the partial product 1 0 1 0, and next step also the partial product become 1 0 1 0, and how are we going to write it? We are basically shift the writing of this next step, end step partial product one step to the right, and introducing a 0 at the left on that stage, and introducing at the 0 at the MSB of the partial product of the previous stage, right? So this is what we are doing so far. Isn't it same as like doing the other way? Okay, first of all, let's also understand one thing, like when we are shifting the product at the end stage, that means we are actually padding up with 0, means the additions of that column will only depend till the partial product of the previous step, right? That product step, that bit plus 0 will give 0, always, right? So it's the same bits. If this bit was 1, then 1 plus 0 would give rise to 1. So we are kind of finalizing the partial product LSB when we are doing the nth step, when doing the next step, right? Now look at this one. Your partial product was 1 0 1 0 and product as nth step as 1 0 1 0. Now just instead of shifting this product 1 0 1 0 at the nth step to the left, why don't we shift the partial product of the previous stage to the right? Okay, and then finalize the bit, whatever that shift product is. Okay, so this is the strategy we are going to apply. Okay, let's review this multiplication on the paper pencil binary, how it's going to work now. So we pick up the first bit, we write down the partial product address step, and then right shift both the partial product and the multiplier. Okay, so multiplier first bit goes out of scope, and you are finalizing the LSB of the partial product. Okay, then do the same thing with the 0. We are adding up. Okay, the partial product 0, we are adding up 4 bits, so that becomes 0 1 0 0, etc., right? And then next step, we right shift both. We are finalizing the LSB of that partial product, and next step we are computing the partial product as well, and then right shift both of them, doing the partial product and sum them, and that becomes my answer. Before that, we need to do one more shift here. Okay, and that gives you this 8-bit. Remember, that was 7-bit, right? We need to complete the 8-bit because this is we must account for all the bits. 2 4-bit will give me 8-bit. So we need to completely make the multiplier out of the scope, shifted out, whereas we are shifting in the partial product as well at the same time. So our value become 0 1 0 0 1 0 0 0. So in terms of, and we can finalize that now because we are done. In terms of register and everything, let's say multiplier is multiplicand stored into the 4-bit, multiplier in the lower half of the 8-bit. So this is the special arrangement register where I can partially load the upper field and together we can shift out. Okay, so multiplier we put in the lower half of the product register. Multiplier, okay, the LSB multiplied with the multiplicand, that becomes your partial sums operands. Then we write down that product here back into that upper half and then shift. Then we do the same thing, add, shift, do the same thing, add, store it back, same thing, add, store it back, and same thing. So essentially, this is my final product, right? So essentially what we are doing is, your multiplier was 4-bit and we are anyway shifting it out. So we are reusing those multiplier bit position at each step so that your partial product is gradually creeping in from the left hand side to the right hand side as multiplier goes out of the scope. So that's what enabled us to kind of compact our hardware circuitry. Now as we understand that strategy, now this logic circuit should make sense to us, right? We are keeping the multiplicand as it is. Then we are performing the multiplications, okay, by replicating the multiplier LSB 32 times, okay, so that if it is 0, it becomes 0 0 0 0 all 32 bit 0. If it is 1, all 1, then we are practically out of this AND gate, either we are getting all 0 or the multiplicand value, right? That's one thing. And then we are adding up as a 32-bit partial product, loading into that partial product, and together we are shifting out the multiplier by 1 bit each step, and the product LSB is being finalized into the multiplier register unused bit. So this is the whole strategy it need to do for the 32 times, and after that controller just says I'm done, and result can be picked up from your 64-bit register.